Okay, so this is the last section of chapter 2, solving problems involving rates of change. This is basically going to be a typical pattern. At the end of every chapter, we're going to be doing one section of solving problems or using rates of change of the different formulas and stuff, the different types of formulas that we're going to be seeing throughout the course. So the last section will be as fun as you can imagine. So this problem is from an example on page 107 in your textbook. So there's a theater company, and the formula for the profit is that negative 60x squared plus 18x plus 16,500, where x is the cost of a ticket in dollars. So what I'd like you to do is we want to find the estimate of the instantaneous rate of change. But first of all, what I'd like to do is fill out that table and finish off the rest of that where the blanks are. And basically what we're going to be doing, just as we've done in the past, the target value is $15, as you can see there. So all the way along here, this $15 is going to be the target value, and then we see for the first, or the profit is going to be 30,000. The profit for that's x2, and then the profit for p of x1 is going to be what those would be if you were to calculate this formula with the values 14 or 14.5 in dollars. And then the rate of change of profit is, as you see there, okay, so as we fill in that table, so the first four calculations is for the preceding interval when the ticket price is lower than the $15 mark. And then we're slowly going to go up towards that $15 mark, so $14.50 and $14.90, followed, of course, by $14.99. And then, so obviously when we're doing these calculations, you don't need to round anywhere past 2 decimal places, because when you're using money, we only go to hundredths, so you just have to round off there. And then we work out what the rate of change of profit is at the different dollar amounts for the tickets. Okay? Can you calculate the same things for the bottom portion of that table, please? Sorry, we're going to be using now the following interval. So the ticket price for x2 is going to be starting at $16, then go down to $15.50. Then $15.10, and then $15.01. Which is already there. Okay, so we see that as we have the preceding interval, as we approach the ticket price of $15, we go from 14 up to $14.99, and the rate of change of profit goes from $60 all the way down to $1. And then in the following interval, we have the ticket price of $15 that stays constant, and then the following interval starts at $16 and decreases down to $15.01, and the rate of change of profit goes from negative $60 down to negative $1. So then if we want to then use these results to estimate the instantaneous rate of change, one would say the estimate of the instantaneous rate of change equals So remember that all of these calculations that you've done in the table, those are all average rates of change, every single one of them. It only becomes the estimate of the instantaneous rate of change when you then take the last two results, the ones that are closest to the target value that you're looking at, in this case $15, and taking the average of those. So we take the average, so we've got 1 plus -1 all over 2, and that gives us 0. Any questions about that? Okay, so remember there's always average rate of change through the entire process until that very last step where you just take the average of the last two average rates of change. And then that becomes your estimate of the instantaneous rate of change. Okay, so then we have, what kind of graph is this? What kind of function is this? Yes? And what does it look like? By looking at that equation, what's the general shape of that? Like, is it opening down, opening up, opening down? Why? How do you know that?
Because it's -60, and negative means the y values will be going down from the maximum rather than going up from the minimum.
Yes. Great, thank you. So, as we take a look at this function, we want to graph that just to kind of take a look at where x equals 15 actually is on the graph. So if we were to graph this, now I know the scale doesn't lend to getting up to 30,000, but if you were to factor out 1,000 from that, like we could just reduce all these values by a factor of 1,000 to get up to 30 there. So if you were to draw the parabola, it should look like that, and then 15 is, it looks like then the midpoint of the zeros, which would be the axis of the axis of the curve. And then if we take that $15 and substitute it into the formula, then we would get 30,000 there. Okay, so try to draw a quick sketch of that. Not really sure what the zeros are here. It's a little bit larger, or a little bit smaller than -7 there. About 37.5 or so for the other zeros. Okay, so on the reverse side of that page, we want to look at the instantaneous rate of change, or what our estimate is, and the location of the maximum. What do you notice about that instantaneous rate of change at that maximum?
Well, the slope is 0, so you can say that because the slope is 0, the maximum point of the parabola was E.
Because the slope is 0? How do you know that?
Because the line that it crosses, touching the 15 point, will only touch 15, and it's completely parallel to the x.
Yeah.
So that says to me that it must be the highest point.
Okay. Yes, that's good. Thank you. Shannon, do you have something else to add, or?
Just the
Okay.
If you plug it in.
Yes, so at x equals 15, the y value there is 30,000, that's the highest point, the highest value. And any other value of x substituted into the formula will give you a lower value, which indicates that 30,000 is the maximum. And so John, what you said about the slope being 0, we have to remember that